Okay, so I've got 2 quarters sitting on the green spinny thing. So as they go around, are the quarters accelerating? Yes, because they are moving in a circle. Now, here's the anomaly about centripetal force. If you look at centripetal force and the 4 fundamental forces, 4 fundamental forces of gravity, electromagnetic, strong nuclear, weak nuclear. Notice that centripetal force is not listed as one of those 4. Because here's what you have to remember about centripetal force. Centripetal force is only manifested through something else. It's manifested through gravity. It's manifested through the electrostatic force that holds the string together as I go around like this, and the friction that I use to hold on to the string. It's manifested through the friction that holds that on. Okay? So centripetal force never exists on its own. It only exists because of something else. Okay? So like if the universe didn't have gravity, there would be no planetary motion to talk about. Because you would have no planets orbiting the sun if you didn't have gravity. We wouldn't be here having this discussion anyway, so it doesn't matter. So here's my question. And again, this is not on your equation sheet. What you have on your equation sheet is that force friction equals mu times force normal. That's what's on your equation sheet. So here's the leap of faith that you need to be able to take. And go, okay, I can play this game. Mu is force friction over force normal. Okay, something you've done countless times. Okay, this is not anything new. But here's what you want to look at. The force friction is what's creating the centripetal force. So instead of force friction, I'm going to write mass times my centripetal acceleration, because that's what that's creating. The frictional force is creating the centripetal force, which is mass times your centripetal acceleration. Force normal on a flat surface, oddly enough, is the same as Fg. So I'm just going to put that as mg. Now at this point, one thing you can do is cancel out the masses. Cool. Okay? So from here, you could go 4 pi squared r over t squared over g. Now, based upon this relationship right here, 4 pi squared r over t squared, I'm going to make this go faster. As it goes around, which quarter is going to have the bigger value of t? The outside one, the inside one, or is it going to be the same?
Same.
Same, because it's on a spinning object, right? So t is going to be the same for both of them. G is going to be the same for both of them. So the only variable is what?
Radius.
Radius. Cool. Okay? So as this spins up, which quarter is going to fly off first? Outside, inside, or the same?
Outside.
Outside. Why? Sydney?
Since the radius is big.
So what? You're right, the radius is bigger. So why does that lead the outside one to fly off first?
It's got a greater mu.
Okay. Is there a limit to what friction can do? Or is friction an unlimited force?
Limited?
Because if it was unlimited, then the quarters would never fly off. Okay? So friction can only provide so much force, right? So as I spin this up, the outside quarter flies off first, because it's going to require the largest centripetal acceleration. So it's going to exceed mu first, because the radius is bigger, it's traveling faster, is going to require a greater amount of frictional force to stay on there. That exceeds that limit first. So, I promise you, there's a question on the review that deals with quarters sitting on like a spinning record. I promise you there's going to be a problem like that on the test. Okay? Promise you. Okay. Now, let's look at vertical motion. Okay? This is the one that you have to be very careful of. So we're going to look at three extremes. What happens at the top? What happens on the side? And what happens at the bottom? So, in all three situations, is gravity acting on the stopper? Yes. Is gravity acting in the same direction in all three situations? Absolutely. Because gravity is a one-trick pony. It's a good trick. But on all of these, Fg is acting straight down. No matter where it is, as this thing goes around, gravity is still acting straight down. Okay? That's it. Only way it can act. In all three situations, does there need to be centripetal force acting on the stopper? Dylan.
Repeat that, I'm sorry.
In all three positions, does there need to be centripetal force acting on the stopper?
Yeah,
Yes. Why?
because you need the tension.
Yeah, because of what's it traveling in?
A circle.
A circle. Mother Nature doesn't like circles. Because if this string broke right here, so imagine that that string breaks right here when it's at completely horizontal. String breaks. Three potential paths it could take. It could travel on path A, it could go straight up on B, or it could curve towards the outside of C. So A is a more gentle radius, B is straight up, C is going to go out like this. Charles, what's going to be the path if I let go of it when it's exactly horizontal? A, B, or C?
Right here.
So imagine this is coming around like this, okay? So I'm going to let go of it when it's at exactly horizontal.
So like when I say B,
B, why?
because there's
Does Mother Nature like circles?
no
No. What does Mother Nature like?
lines.
Straight lines. Okay? So if you chose B or A, you're going to say, oh, gravity, it remembered it was on a curve, it's just not going to curve as much. Okay? That doesn't make any sense. C, you're going, oh, well, there's a force that's pushing it to the outside. That doesn't make any sense either, which only leaves you with
B.
B. Okay? So, this is why there has to be a centripetal force. So, Connor S., when it's at B, I've got gravity acting straight down. What's the other force acting on it when it's at B?
I mean, are we talking about when it's like still attached to the string or not?
No, when it's here at its side. I'm sorry, I confused, I screwed that up. When it's at this point right here,
Okay, so it's centripetal force.
acting which way?
Inward.
Inward. Okay, so I got gravity trying to pull it down. I got centripetal force acting that way. Okay? Up at the bottom, when it's down below, do I have to have some centripetal force acting on it there? Yes, because if I don't, what's it going to do? It's going to go turn into a lemming problem, right? So at the bottom, this is when you add these. So your total force at the bottom is Fc plus Fg. And don't get hung up on making one negative and positive. Just add the numeric values together, okay? Because you're talking about the inward force created by the tension in the string. This is why any equation has to be able to work under any circumstance. So right now, if I just hold this thing, how much total force is the rubber stopper going to feel? Gravity. It's just going to feel its normal weight, okay? The string just has to balance out the weight of the stopper. That's it, nothing else. Now, I make it swing in an arc, then what's going to happen to the force when it's at the bottom? Increase or decrease? Look at it. If I swing this thing around like this, what's going to happen to the force at the bottom versus if I'm just holding it?
What?
Okay, I got this thing going around like this, okay? Versus this. When is there going to be more tension on the string? When it's like this
Spinning,
or like this? Why?
because it's gravity and the centripetal force.
Beautiful. So it's going to feel heavy. So you cannot be in a state of weightlessness at the bottom. Okay? Because even if you're not moving at all, like right now, you all are experiencing 1G. So even at the bottom, if there is no centripetal force, you're still going to feel the force of gravity. Okay? That's what you all are experiencing right now. Now, if we add them at the bottom, what are we going to do at the top? Force total is going to equal Fc minus Fg. Now again, neither one of these equations are on your big dog equation sheet. Okay, they're not there. But this is where you have to be able to rationalize it out and go, yeah, right, okay, I'm at the bottom, I'm going to feel heavy. I'm going to add them. The top, I'm going to subtract it. And it's like the alphabet. Centripetal force comes before your gravitational force. Okay? So Fc minus Fg. So this is the one where you can feel like a fraction of your weight. And you all did a problem like this. So for example, I might say, all right, I want that rubber stopper at the top to feel 1/4 its normal weight. I want it to feel 1/4. So you'd have 1/4 equals Fg, and then you have centripetal minus Fg. So mathematically, what's the first thing that you have to do?
Add the FG to the other side.
And that's going to get you,
5/4.
and I'm going to put that as mg equaling mv squared over r. What's going to happen to the mass?
Cancel.
So you get v equals the square root of 5/4 GERD. The only thing I can change in this problem is that fraction. Okay, that's it. That's the only thing I can change. I can make it a half, I can make it 3/4, I can make it 7/16. Okay? That's the only variable that I can change. Is it possible for this side to equal 0? Yes, you would be in a state of weightlessness, which is what happens when you're in orbit. Okay? Because when you're in orbit, the centripetal force is just creating the gravitational force. Okay? All right. So, promise you, there's going to be questions like that. Promise you, promise you, promise you. Promise you there's going to be a question where something's on a turntable going around like this. Promise you that's going to be there. Promise you there's going to be the one where you're going to have like the conical pendulum like this going around. Promise you that's going to be there. Now, when you get to the planetary motion part of this, okay? So here's the basic idea, is that the gravitational force that you're going to experience is what's creating the centripetal force. This is what allowed, like for example, when we put Luke into orbit, that was the mass of Luke times the mass of the Earth over r squared, which equaled mass of Luke v squared over r. So what's going to happen to Luke? Luke is going to cancel out. Okay? Whether it's the orbital period, whatever that is, Luke is going to cancel out. But that leads you to a bigger truth, that centripetal acceleration is equal to your gravitational acceleration, okay? Because the masses are going to cancel out. So that's what allows us to come up with that big Swiss Army knife equation. It allows us to come up with this. It allows us to come up with little g. Now, I want to make sure everybody's cool with two different equations. So you have little g equals big GM over r squared. You also have that mass 4 pi squared r cubed equals big G. No, that's 4 pi squared r cubed. Big G mass times t squared. Okay? Understand when you use each one. So this would be, hey, we land, you're the science officer on a space probe. And you land on a planet, okay? And you somehow figure out the acceleration due to gravity when you land on that planet. And you want to find the mass of the planet itself. So this mass here, if you're invoking little g, is going to be that gravitational acceleration. This mass would be a star's mass at the center of an orbit, or this moon orbiting around a larger planet. So understand which one is which. So this one, you might say, oh, here's this planet orbiting around the sun, find the mass of the sun. This one you would say, oh, we land on the planet, let's figure out the mass of the planet. Okay? So be very cautious about that you understand which one is which. I promise you there's going to be a problem where you're going to have like a satellite or something that's going to orbit the Earth. Okay? I might give you the orbital period. I might give you the orbital radius. Okay? Something like that. But what value am I never going to give you? Dylan.
The mass of the satellite.
I'm never going to give you the mass of the satellite. Why?
Because
Doesn't matter.
It doesn't matter. It drops out of the equation. Okay? So remember that, remember that, remember that. Where is every radius measured?
From the center.
Center to center. But you have to be careful of the wording. So if I tell you, like for example, one of the things you're going to calculate is when you hand in the test, if you have not calculated the orbital period of the lunar command module as it goes around the moon, you have done something horribly wrong. Okay? So I'm going to tell you that it's so many kilometers above the moon, and then I'm going to give you the radius of the moon. So what are you going to do? Add them together and then do what? Convert it in, because those are going to be in kilometers, so those has to be converted into meters. Anything that's orbiting the moon, anything that's orbiting the Earth, what should the order of the exponent be for velocity? Something times 10 to the third. What about orbital period in seconds? Something times 10 to the third. Okay? You don't even have to remember different numbers. Okay? You don't even have to remember different numbers. Oh, orbital period, 10 to the third. Velocity, 10 to the third. Okay? Make sure that you understand those concepts of ratios. Okay? Like being able to use a ratio to figure out like the orbital period or the mass of the center or something like that. Okay? If you hand in the test and you haven't like done that, you have done something horribly wrong. Okay. All right, so let me stop that. Let me hand out the review and tell you what's relevant and what's